Come with me for a moment. Imagine you're holding a tiny seed in your hand, a tomato seed perhaps. It feels insignificant, a dormant promise weighing almost nothing. But this isn't just any seed, it's about to embark on a journey beyond our world, leaving behind the blue skies and rich soil of its home. This seed is a pioneer, an astronaut in its own right, carrying the blueprint for life into the cold, silent emptiness of space. It represents a question: can we nurture life where there is none? This seed's journey is our journey. Its voyage began not with a rocket launch but with hope, a hope that we could sow our future among the stars. We packed our dreams and survival into these tiny vessels, sending a message to the cosmos: we are here, and we intend to grow. Think of the forces this seed will endure, the violent vibrations of liftoff, the crushing pressure of acceleration, and then sudden weightlessness. It floats, untethered from gravity, in a place where up and down have no meaning, and sunlight is a harsh, unfiltered glare. Its destination? A small, pressurized module orbiting our planet, a laboratory, a greenhouse, a sanctuary in the void. Here it will be asked to awaken, to unfurl its first leaves under the sterile glow of LED lamps, and send its roots searching into a nutrient-rich mist. This seed is a testament to human ingenuity and our instinct to cultivate. Its journey from your hand to the stars is the first chapter in a story of survival. It's how we learn to garden on the edge of forever. This is more than a scientific experiment, it's a leap of faith. The seed's voyage is a symbol of our determination to thrive no matter how far we travel. In its tiny shell it carries not just life but the hope of a future among the stars. And so, the story begins, with a single seed and the courage to let it go. Why send a seed on such a perilous journey? To answer that, we must look down at Earth in the early 2020s. Our planet was groaning under our weight. Climate change was accelerating, farmlands turning to dust, and unpredictable weather made farming a gamble. The breadbaskets of the world were emptying. We were billions, and we were getting hungry. Aquifers ran dry, seasons became chaotic, and food shortages led to instability and soaring prices. We realized we'd placed all our bets on a single fragile world. If we were to venture beyond Earth, we couldn't rely on resupply missions from a struggling home. We had to learn to become farmers of the cosmos. The dream of space exploration became entangled with the necessity of survival. Space offered the ultimate challenge. Could we grow food in a sealed environment, recycling every drop of water and nutrient? Solving this wasn't just for astronauts. It was a blueprint for a new kind of agriculture on Earth. The quest for space farming was born from a terrestrial crisis. We turned our gaze upward, not to escape, but to learn how to save our home. We had to leave the garden to learn how to save it. The seed's journey was our desperate, audacious plan for survival. The first attempts at space farming were humble, filled with nervous anticipation. Astronauts became gardeners, tending to small, high-tech chambers called veggie. They planted lettuces and radishes and zinnias, plants chosen for speed and resilience. Injecting water into specialized clay soil, they switched on LED lights, bathing the habitat in magenta glow. In the sterile environment of a space station, the sight of a green sprout was a miracle, a living piece of home. Astronauts would hover by the growth chamber, watching leaves unfurl, reconnecting with the cycles of Earth. The scent of growing plants, faint and earthy, was a beautiful reminder of rain on soil. The first harvest was pure joy. The crew of Odyssey tasted the first red romaine lettuce grown entirely in space. They didn't just eat it, they celebrated. Each member got a single leaf, toasting to self-sufficiency and the future. It was a bite of food that hadn't been freeze-dried or shipped from Earth. It was alive. These early experiments were more than scientific milestones, they were deeply human moments. Astronauts became caretakers, emotionally invested in their tiny crops. That patch of green became the psychological heart of the station. It proved we could carry the impulse to plant a seed and watch it grow, even into the void. The first sprouts in space were a promise. Life could follow us wherever we dared to go. Each leaf was a victory over emptiness, and with every harvest, hope grew alongside the plants. Growing life in space was never as simple as adding water and light. The cosmos presented invisible challenges. Chief among them, gravity, or the lack of it. On Earth, gravity guides roots down and shoots up. In orbit, plants grew confused, roots curling in all directions. Water formed floating spheres, threatening to drown or starve the roots. Scientists developed plant pillows, sealed bags with porous clay to hold water around the roots. Wicks and slow-release fertilizers delivered nutrients without mess. Sunlight in space is harsh, Inside the station there is none. LEDs provided the exact wavelengths for photosynthesis, creating the magenta glow of space farming. Watering had to be precise. Closed-loop hydroponic and aeroponic systems were developed, using up to 90% less water than traditional agriculture. Microbes and fungi, stowaways from Earth, could flourish in the warm, humid chambers, threatening crops and life support. Advanced scrubbers and monitoring systems became essential. Every variable, CO2, humidity, temperature, nutrients, had to be perfectly controlled. Overcoming these obstacles turned astronauts into meticulous gardeners, blending science, engineering, and a farmer's watchful eye. Each solution in space became a lesson for Earth. The cosmic garden demanded innovation at every turn. The success of orbital gardens sparked a new ambition. Could we grow fields on the moon? At Armstrong Base, lunar farming meant building shielded, inflatable habitats buried under regolith for protection. Inside, AI-driven systems and robotic arms managed every aspect of planting, pruning, and harvesting. Hydroponics and aeroponics, perfected in orbit, became the foundation of lunar agriculture. Multi-level vertical farms maximized space, recycling water with near-perfect efficiency. Crew waste was processed by bioreactors, feeding plants in a closed loop. Within a decade, Armstrong Base produced over 70% of its own food. Potatoes, soybeans, wheat, tomatoes and more. Golden wheat swaying under LEDs deep beneath the lunar surface became a symbol of human tenacity. The tiny pots in orbit had blossomed into fields on the moon. For the first generation born on the moon, food was fundamentally different. Farm to table meant a walk down the corridor to the biodome. Apples grew on vertical trees, potatoes were harvested by robots. Fresh salad was normal, not a luxury. The psychological impact was profound. The first lunar pizza, wheat, tomatoes, basil grown on the moon, became a celebration of independence. Every calorie was precious, every harvest a triumph. Children learned the science behind their meals, respecting every drop of water and joule of energy. Waste was unthinkable. Their garden was their lifeline. The first meal shared between an Earth-born astronaut and a moon-born child was poignant. Two perspectives converging over a space-grown meal. For the astronaut it was a marvel. For the child it was simply lunch. In that moment, humanity's relationship with nature evolved. The taste of starlight became the taste of home. The innovations born from space farming didn't stay in space. They came home. Closed-loop systems and vertical farming, powered by efficient LEDs and AI, began to revolutionize agriculture on Earth. Farms appeared in deserts and on city rooftops, using a fraction of the water and land. Immune to droughts and pests, these farms provided fresh produce locally, slashing transportation emissions. Aeroponic and hydroponic systems turned barren landscapes into productive centers, easing the water crisis. Advanced recycling techniques from lunar bases provided clean water for cities. By solving for survival in space, we found solutions for sustainability on Earth. The impact went beyond technology. It shifted our perspective. We learned to produce abundance with care, minimizing our footprint. The seeds of innovation from the stars helped heal the world we once struggled to leave. This journey, from a single seed to lunar farms, is a story of hope. In a time of crisis, we chose to plant a garden in the most audacious place imaginable. That first sprout in orbit was a fragile affirmation of life's tenacity. Space agriculture inspired a new generation to tackle Earth's challenges with creativity. Cultivation is an act of hope, a pact with the future. By planting seeds on the moon, we planted hope for a future beyond Earth. The lunar farms fed more than bodies, they fed our collective soul. Humanity's adaptability was tested and proven. We learned that home is not a place but a set of principles: care, cultivation, and continuity. The harvest of hope we reaped from the stars is ours to share. We return to that single seed, its journey now complete. From Earth's soil to orbit to the moon, it has been nurtured by human hands and robotic arms. It has fed pioneers, taught children, and sent its lessons back to Earth. This seed is no longer just a seed, it's a story of our evolution. For millennia, we've carried seeds across continents now. We carry them to the stars. Seeds sent to Mars and beyond are not just for food, they are living pieces of Earth, cultural ambassadors. Each one is a promise: wherever humanity goes, life will follow. These seeds hold the potential for new beginnings on worlds we can only dream of. Space agriculture has expanded our reach and our sense of what's possible. The next time you hold a seed, remember its cosmic destiny. The most powerful forces are often the smallest and quietest. Sometimes they are just a tiny seed waiting for its chance to grow. Our future is written not just in the stars but in the seeds we carry with us. Have you ever stopped to consider if a plant, rooted in Earth's embrace for millennia, can miss the sun? Not with human-like memories, of course, but in a deeper, more fundamental way, a biological yearning, perhaps. Does a seed, bravely germinating far above Earth in the cold vacuum of space, sense the profound absence of that ancient star, our sun, that has shaped and sustained life for billions of years? Down on Earth, every leaf, every stem, and every root is an integral part of a grand, ongoing conversation with the sun, a silent dialogue of light and life, dictating the rhythm of life, the blooming of flowers, the shedding of leaves, and the turning of seasons. In space, however, that vital conversation falls silent, replaced by the hum of machines. For decades, the reality of space travel meant strict rationing, a constant awareness of limitations, every precious drop of water, every carefully measured breath, and every single calorie consumed. The idea of growing food in space was once a distant dream, deemed too expensive, far too complex, and simply impractical. Early astronauts were essentially visitors, temporary inhabitants of an alien realm, completely tethered to the constant resupply of vital resources from home, with Earth serving as their distant pantry and ever-reliable well. But humanity, in its relentless pursuit of progress, isn't content to merely visit. We're inherently driven to stay, to explore, and to establish a permanent presence. The monumental leap from simply surviving to truly living and thriving in space ultimately meant severing that crucial umbilical cord to Earth and embarking on the ambitious endeavor of building a miniature, self-contained Earth in the vast void. The ultimate challenge to create a completely self-sustaining ecosystem, a closed-loop life support system, without the benefit of fertile soil, natural rain, or the gentle warmth of a sunrise. By 2047, we're no longer just temporary visitors. We've become dedicated gardeners diligently cultivating life in the void. On advanced stations like Gaia Spire and Artemis Base orbiting far above our home planet, the invigorating scent of fresh basil and the sweet aroma of ripe tomatoes delicately mingles with the carefully recycled air. This remarkable transformation is a symphony of groundbreaking innovations, a testament to human creativity, a compelling story of how we learned to skillfully mimic Earth's essential life-giving processes. It's the inspiring story of how we dared to build a flourishing garden at the very edge of forever, a powerful testament to the boundless capacity of human ingenuity and our unwavering determination to thrive amongst the stars. The shift from mere survival to a truly sustainable way of life in the vast expanse of space was a profound and fundamental transformation. It marked a turning point in our cosmic journey. It was like learning to breathe underwater, adapting to an entirely new and alien environment. For nearly a century, astronauts existed as walking ledgers of consumables, meticulously tracking every single gram and drop of resource, accounting for its use and potential for recycling. The logistics of keeping these brave explorers alive were staggering, a monumental undertaking. In that context, a simple, ordinary apple was as precious as gold, a symbol of life and sustenance. But to truly explore the depths of space, to reach for the stars, we had to stop packing bigger and bigger suitcases, and instead, learn to live off the land, to cultivate and harvest what we needed from our surroundings. Even when that land was a vacuum, a seemingly barren and hostile environment. Space farming wasn't just about having access to fresh, nutritious food, it represented true independence from constant resupply missions, a critical step towards self-sufficiency. Communities that could successfully grow their own food, efficiently recycle their precious water resources and reliably generate breathable air, were communities that could truly endure, thrive, and ultimately expand their reach into the cosmos. The journey, the evolution from a few stunted, struggling plants on the International Space Station to the advanced agricultural modules we see in operation by 2047 was a long and arduous one filled with countless setbacks and failures along the way. We had to fundamentally change our perspective to become the soil, the rain, and the life-giving sun for these fragile ecosystems. The true leap forward happened when we shifted our focus from simply keeping plants alive to actively building and nurturing environments where they could truly thrive and flourish. We transitioned from a model of mere life support to one of active life creation, mastering the art of generating and managing oxygen, carefully conserving and recycling water, and replicating the power of sunlight, all within the confines of a tin can, hurtling through the void. This monumental achievement gave us a fundamental blueprint for self-sufficiency in space, and instilled in us the confidence, the unwavering belief, to venture even further into the vast and mysterious cosmos. At the heart of this revolution is the artificial trinity: oxygen, water, and sunlight. On Earth, they're invisible gifts. In space, they must be manufactured with precision. Mastering these three elements unlocked permanent space habitation. The breakthrough came when we treated them as an integrated dynamic system. The oxygen we exhale feeds the plants, the water they transpire is reclaimed, the light we generate powers photosynthesis. This interconnectedness is the definition of an ecosystem. By 2047, space farms are sophisticated ballets of technology and biology. We set the day's length, the air's composition, the timing of rain. We are the creators of tiny bespoke worlds, sustaining life far from any natural ecosystem. The artificial trinity is more than engineering. It's a new genesis. It transforms fragile outposts into resilient colonies. It's the engine of our expansion into the solar system. Oxygen, the very essence of life, is the fire that fuels our existence, unlocking the energy stored within our food. It's the key to cellular respiration, the process that keeps us going. On Earth, oxygen is remarkably abundant, a vital component of our atmosphere, creating the beautiful blue skies we know and love. But in the vastness of space, it's a different story. Early space missions relied on carrying oxygen in heavy, finite tanks, a precious resource that had to be carefully managed. For establishing permanent settlements beyond Earth, a regenerative source of oxygen became absolutely essential for long-term survival. The ingenious solution? Water. Through the process of electrolysis, we can split water molecules into their fundamental components, oxygen and hydrogen. And this entire process is efficiently powered by the abundant sunlight captured by solar panels. Space stations such as Gaia Spire are equipped with advanced electrolysis modules that run continuously, ensuring a steady supply of breathable air. Furthermore, these stations employ sophisticated water reclamation systems, meticulously reclaiming water from breath, waste, and even plant transpiration. The hydrogen, a valuable byproduct of electrolysis, isn't wasted. It's used for propulsion, powering rockets and spacecraft. Alternatively, the hydrogen can be combined with carbon dioxide, CO2, to produce methane and, crucially, even more water. But the true stroke of genius lies in our partnership with biology, harnessing the power of living systems. Plants, through the miracle of photosynthesis, inhale CO2 and exhale oxygen, effectively creating a self-sustaining closed-loop ecosystem. The CO2 exhaled by the crew is carefully piped to the crops, providing them with the raw materials they need to thrive. These plants, bathed in the glow of artificial sunlight, efficiently convert the CO2 into the fresh, breathable oxygen that sustains the crew. To ensure optimal conditions, thousands of sophisticated sensors constantly monitor the atmospheric balance. The Environmental Control and Life Support System, or ECLSS, diligently keeps everything in perfect check, maintaining a stable and healthy environment. If there's too much or too little of any particular gas, the system automatically adjusts, ensuring a safe and comfortable atmosphere. We've come a long way from simply carrying air in bottles. Now, we're actively cultivating it in lush, thriving space gardens. This represents a profound step forward, paving the way for true, long-duration spacefaring and exploration. Our air is no longer just stored, it's actively grown, a testament to our ingenuity and a vital component of our future among the stars. Water in space is more precious than any metal. Every drop is recycled. In 2047, every molecule is part of a closed-loop system. The water you drink today may have been in your crewmate's breath or a tomato plant an hour ago. Water reclamation systems capture moisture from air, sweat, and even urine, purifying it to the highest standards. The water processor assembly is the station's mechanical kidney, endlessly renewing the supply. For plants, traditional irrigation won't work in zero gravity. Hydroponics and aeroponics deliver water directly to roots, no waste. Hydroponics suspends roots in nutrient-rich water. Aeroponics mists roots with nutrients, using up to 98% less water than earth farming. Roots hang in air, periodically vanishing into a life-sustaining mist. It's a ghostly, beautiful sight. Green plants floating, roots shrouded in fog. This is water in space, not a flood, but a precise, sustaining whisper. Every drop is accounted for, every cycle closed. This is the foundation of orbital life. Creating an artificial sun is more than flipping a switch. Sunlight is a spectrum. Plants need blue for growth, red for fruiting, and even invisible wavelengths. Early space farms used white lights. Plants grew pale and weak. The breakthrough advanced LEDs, tunable to any wavelength. Space farmers now paint with light, dialing up blue for lettuce, red for tomatoes, optimizing every stage. This control changes not just growth, but flavor and nutrition. Specific light recipes coax more vitamins or aromatic oils from plants. We simulate dawn and dusk, optimizing photosynthesis. The artificial sun never sets unless we command it. Day and night are manufactured, cycles tailored for each crop. We've distilled the chaotic power of a star into a precise tool for life. Step inside an agricultural module and you leave the metallic world behind. The air is humid, alive with the scent of green things. Racks of plants stretch from floor to ceiling. Some in hydroponic trays, others in aeroponic mist. Pumps, fans, and sensors hum quietly, maintaining balance. The station's AI manages the core systems, but human farmers are essential. They check for stress, prune leaves, pollinate by hand. Each crop has its quirks. Strawberries need precise light, spinach thrives with little help. This high-tech garden is fragile. A single failure can spell disaster. Farmers live with constant awareness, running diagnostics and maintaining hardware daily. They're not just growing food, they're sustaining a miracle of engineering. This glass garden, glowing purple, is a symbol of our foothold in space. It's beautiful, productive, and endlessly complex. The ultimate goal of a space farm is a perfect circle, a fully closed-loop system. Every output becomes an input. Nothing is wasted. Crew waste is processed into water and nutrients CO2 is converted by plants into oxygen. Inedible plant matter is composted or recycled. On Earth, nature is chaotic and redundant. Space farms are streamlined, optimized, and have almost zero redundancy. Is this still nature or something else? When machines meet every need, is a plant still part of a natural process? It's alive but completely dependent on technology removed from Earth's wild web. No seasons, no pests, no droughts, life without struggle, but also without wildness. Perhaps we're redefining nature, not soil and wildness, but the fundamental processes of life, wherever they occur. Space farms are hybrid ecosystems, a fusion of biology and technology. In building these circles, we reflect on our relationship with nature itself. The technologies we developed for space are transforming farming on Earth. Closed-loop water reclamation and aeroponics, born in orbit, now thrive in arid regions. Vertical farms use these methods to grow fresh produce year-round, using less water and land. Tunable LEDs, perfected in space, revolutionize indoor farming, optimizing yield, flavor, and nutrition. We're no longer bound by the sun's schedule. Food can be grown anywhere, anytime. The greatest lesson is perspective. Earth is a vast, finite life support system. Building tiny biospheres in space deepened our appreciation for Earth's robust, self-correcting one. We've learned resources aren't infinite. Closed-loop systems are key to sustainability. The dream of cultivating new worlds has taught us to be better stewards of our own. The principles of survival are universal, whether tending a garden in orbit or protecting a planet in the cosmos. Imagine tending a small garden, a peaceful sanctuary where life flourishes with minimal effort. Rich soil teeming with life, earthworms aerating the earth, and a microscopic universe of soil microorganisms working in harmony. The sun's energy and the gentle rain, all working together in a delicate balance to nurture growth. Here on Earth, our planet's ecosystem does most of the work for us, a natural partnership that sustains life. Now picture yourself on the Moon or Mars, far from Earth's nurturing embrace. You're inside a pressurized dome, a fragile haven, staring out at a barren, alien landscape, a world devoid of familiar comforts. Your mission: grow food, to cultivate life in an environment that seems determined to resist it. But here the ground is not soil, the life-giving foundation you're accustomed to. It's regolith, lifeless dust created by countless cosmic impacts over billions of years. No worms to enrich the earth, no microbes to break down organic matter, no life-giving rain to quench the thirst of the land, just sterile powder, an inert substance that offers no natural support for plant life. This is the cosmic gardener's dilemma, a challenge unlike any faced before. How do you create life where there's never been any? How do you coax sustenance from a substance so utterly devoid of it? It's not just about adding water and sunlight. It's about understanding the intricate dance of biology and chemistry. It's about building an ecosystem from scratch, a self-sustaining cycle of life inside a bubble on a hostile world. Every tool and technique we know about farming must be reinvented, adapted, and pushed to its absolute limit. We're not just gardeners, we're pioneers. explorers of the biological unknown. We're writing the first chapter of biology on another world, a testament to human ingenuity and resilience. The stakes are high, the success of future missions depends on our ability to solve this challenge. To settle the moon or Mars, to establish a permanent presence beyond Earth, we can't rely on endless supply ships from Earth. A greenhouse is more than a food source. It's a declaration of independence, a symbol of self-reliance. It means sustainability, self-sufficiency, and the hope of making a true home away from home, a place where future generations can thrive. Growing food in alien soil is about more than nutrition. It's about psychological well-being, about maintaining a connection to Earth. It's about proving we can bring a piece of Earth's biosphere with us, a reminder of our origins and a promise of a shared future. It's about learning to thrive, not just survive among the stars to create a new chapter in the story of life. The challenge is monumental, demanding innovation and collaboration, but the reward is the future of humanity beyond Earth, a future filled with possibility. Every seed planted is a step toward a new world, a symbol of hope, and a testament to the enduring power of life. The journey begins with transforming dead rock into living soil, a process of alchemy that will redefine our understanding of what's possible. This is the frontier of cosmic gardening, a bold endeavor that will shape the destiny of humanity among the stars. Let's examine these alien soils, these otherworldly grounds that could one day feed future space explorers. We're not just talking about dirt, we're talking about the very foundation upon which we might build off-world settlements. The moon's regolith is sharp, abrasive dust, a product of billions of years of relentless bombardment. Micrometeorites have pulverized it for eons, relentlessly impacting the surface, leaving jagged, glass-like shards scattered across the landscape. These tiny projectiles have shaped the very nature of the lunar surface. Lunar dust is electrostatically charged, clinging to everything it touches and posing significant health risks to anyone exposed. It gets into seals, clogs machinery, and can irritate the eyes and lungs. Martian regolith is different, bearing the marks of a planet with a more complex geological history. Shaped by ancient water and wind, it's finer, iron-rich and tinted red by iron oxide, giving the Martian landscape its iconic hue. This rusty color is a testament to the planet's past, but Martian soil is laced with perchlorates, a hidden danger lurking beneath the red surface. These are chemicals toxic to humans and plants, a significant obstacle to any attempts at Martian agriculture. Any crops grown here would absorb these toxins, drawing them up through their roots, making them unsafe to eat without extensive treatment and processing. Both regoliths are chemically inert and nutrient-poor, lacking the essential elements that plants need to thrive. They're essentially crushed rock, not true soil in the biological sense. They lack the organic matter and microbial life that make Earth's soil fertile, a complex ecosystem that supports plant growth. Growing a potato in pure regolith is like trying to live on vitamin pills made of stone. You might survive, but you certainly won't thrive. On the moon, the main threat is physical, a constant barrage of micrometeorites and extreme temperature swings. It's the sharp, clingy dust that damages equipment and lungs, a persistent nuisance that requires constant vigilance. On Mars, it's chemical, a more insidious danger that requires careful mitigation. It's the toxic perchlorates and a lack of nutrients, a double whammy that presents a significant challenge to agriculture. Neither is soil as we know it, the rich, life-sustaining medium that covers much of our own planet. They're blank, hostile canvases, waiting for us to find a way to bring them to life. To farm here, we must understand each world's unique challenges, its specific limitations and opportunities. Solutions for lunar farming will differ greatly from those for Mars, requiring tailored approaches to overcome the distinct obstacles each world presents. The first step is learning the character of each alien ground, understanding its composition, its properties, and its potential. Only then can we hope to grow life where none has existed before, transforming these barren landscapes into thriving gardens among the stars. Step into a Martian greenhouse in 2049. The air hums with life support systems, and under LED lights, green plants thrive against the red landscape. The astrobotanist is part farmer, part scientist, part engineer. Her tools are sensors, spectrometers, and robotic arms. Each day starts with data monitoring pH, moisture, and plant health in regolith test beds. She battles the alien medium, testing soil reactors to remove toxins, monitoring water chemistry, and observing how earthworms adapt. Every observation is logged, every failure is a lesson. Crops may wilt, roots may struggle, but each setback is critical data. The astrobotanist shares findings with Earth, building a global knowledge base. This is high-stakes gardening, where every leaf and drop of water counts. Together, these experiments slowly unlock the secrets of farming on other worlds. Alien soil challenges go beyond simply missing the familiar nutrients that Earth-based plants rely on. The very composition of these soils presents unique obstacles. The chemistry and structure are formidable, requiring innovative approaches to overcome. Understanding these properties is the first step towards creating viable growing conditions. On Mars, perchlorate are the main villain. These chemical compounds are distributed across the Martian surface. Widespread and toxic, they must be removed or neutralized before crops are safe to eat. The presence of perchlorates poses a significant hurdle to Martian agriculture. Washing regolith with waterworks, effectively dissolving and removing perchlorates, but water is precious in space. Every drop counts and must be carefully managed. Bioremediation with bacteria, using microorganisms to break down perchlorates, is an elegant solution, but complex to implement and control in an alien environment. The goal: detoxify efficiently, with minimal resources and at scale, ensuring a sustainable food supply for future Martian colonists. On the Moon, the danger is physical, a stark contrast to the chemical challenges on Mars. Lunar regolith is like microscopic glass shards, a fine powder composed of sharp, abrasive particles. These shards slice and stress roots, stunting growth and hindering the plant's ability to absorb nutrients. The dust clogs plant pores, blocking sunlight and hindering photosynthesis, damages equipment and threatens astronaut health, posing a constant operational challenge. Its electrostatic charge makes it cling everywhere, adhering to surfaces and making removal incredibly difficult. Defying simple cleaning, the lunar dust stubbornly resists traditional methods. Engineers are developing advanced filters and magnetic shields to combat the clinging dust. These technologies are crucial to protect plants and people from the harmful effects of lunar dust exposure. Overcoming lunar soil's razor edge requires both mechanical solutions, like physical barriers, and botanical innovation, such as developing resilient plant varieties. Both worlds demand creative solutions, pushing the boundaries of science and engineering. Whether it's detoxifying Mars's chemically challenging soil, or shielding against the abrasive lunar dust. The path to extraterrestrial farming is as much about engineering, designing systems to manage these hostile conditions, as it is about biology, understanding how plants can adapt and thrive. Each challenge pushes us to invent new ways to nurture life in environments previously considered uninhabitable. The future of space agriculture depends on mastering these hostile soils, unlocking the potential for sustainable food production beyond Earth. Only then can we truly cultivate new worlds, establishing thriving settlements and expanding humanity's reach among the stars. Beyond soil, alien environments test our ingenuity. Gravity is a major factor: 1/6 on the Moon, 1/3 on Mars, affecting water flow, plant strength, and air circulation. Water drains unpredictably, risking root rot or drought. Plants may grow weak, lacking Earth's gravitational cues. Air stagnates, so robust fans are needed to prevent mold and stress. Martian dust storms can last weeks, blocking sunlight and straining power supplies. Greenhouses must rely on artificial light and advanced filtration to keep dust out. Extreme temperatures are another hurdle: wild swings on the Moon, relentless cold on Mars. Insulation is critical. Materials like aerogel trap heat while letting sunlight in, a vital innovation for survival. Every aspect of the environment must be engineered for life. The challenge is relentless, but each solution brings us closer to sustainable off-world farming. Adapting to gravity, dust, and cold is as crucial as conquering alien soil. Only by mastering all these factors can we hope to grow food beyond Earth. Scientists and engineers are modern alchemists, turning dead rock into living soil. The first step: amend regolith with organic waste. Composted food scraps and human waste become vital nutrients. Biochar, a porous charcoal, helps retain water and provides a home for microbes. Robotic systems could mix regolith, biochar, and compost before humans arrive. The real breakthrough is harnessing life. Extremophile bacteria and fungi that fix nitrogen, dissolve minerals, and form symbiotic relationships with plants. These microbes could create a self-sustaining soil ecosystem. We're also redesigning crops, using gene editing to make plants salt-tolerant, light-efficient, and able to thrive in abrasive regolith. This isn't unnatural, it's accelerating adaptation for survival. The future of space farming lies in blending biology, engineering, and creativity. With each innovation, we move closer to growing life on new worlds. The path to a Martian farm is paved with trial and error. On Earth, labs use regolith simulants to mimic Moon and Mars conditions. Early experiments show plants can grow in treated simulant, but nutrients deplete quickly. Closed-loop systems are essential. Failures reveal new problems, water forms crusts, high pH locks nutrients, and irrigation must be rethought. Each setback is a step toward a solution. Breakthroughs are happening. Soil reactors that detoxify regolith, bacteria that boost growth, and integrated systems combining multiple innovations. The most promising results come from complex, layered solutions. These experiments offer the first real glimpses of sustainable off-world farms. Persistent, iterative science is turning the dream of space agriculture into reality. Growing food on another world is as much a human challenge as a technical one. A greenhouse offers astronauts comfort, routine, and a vital connection to Earth. But trust is key. Can you eat a potato grown in once toxic soil? Rigorous testing and transparent data are essential for confidence. The astrobotanist's responsibility is immense. Failure threatens not just food, but morale and survival. Eating the first Martian-grown salad will be a leap of faith and a milestone for humanity. It marks the moment we begin to put down roots on a new world. The taste of home becomes the taste of the future. The race to master alien soil is a race for the future, economic, political, and scientific. The first to farm off-world gains a strategic edge, making colonization feasible. Should we standardize methods or encourage innovation? The debate is as lively as the science. Every experiment brings us closer to becoming a multi-planetary species. The lessons learned will help us farm deserts and heal Earth too. The story of alien soil is one of adaptation and hope. From a single seed in treated dust, grows the potential for new civilizations. With every sprout, we move closer to making the universe our home. Ever wondered what a potato grown 140 million miles from Earth tastes like? It tastes like victory, survival, and the future. On October 12, 2050, Commander Eva Rostova took the first bite of a Martian-grown potato, and humanity became a two-planet species not just with rockets, but with roots. This meal was more than food. It was a declaration of independence from Earth's fragile supply chain. The journey to that first bite was anything but simple. It began with a question: how do you feed people on Mars? Shipping every calorie from Earth was impossibly expensive and risky. We had to learn to live off the land to plant seeds instead of flags. This was the real leap, transforming Mars from a place of exploration to one of cultivation. Let's dig into the story how we turned red dust into fertile ground. We'll meet the scientists, the setbacks, and the breakthroughs that made it possible. This isn't just about agriculture, it's about human ingenuity and our need to make a home wherever we go. It's the story of how we learned to farm on another world, and in doing so learned more about our own. Martian agriculture was once pure science fiction, lush canals and alien crops in novels, but reality was harsher. Mars's atmosphere was thin, cold, and its soil toxic. For decades, experts dismissed farming there as fantasy. But rover data changed everything. The regolith was hostile, but it held essential nutrients. The problem wasn't missing ingredients but the wrong recipe. Suddenly, impossible became difficult engineering problem. Experiments with Martian soil simulants began and most failed. Plants sprouted, then died. The soil was like battery acid. Yet the pioneers of Martian botany were relentless. Inspired by extremophiles on Earth, they believed life could adapt. Each failed crop was a lesson, not a defeat. They learned from every dead plant, slowly rewriting the rules of farming. The dream of a green Mars survived one experiment at a time. They weren't just scientists, they were explorers of a new frontier, and they refused to give up. At first we tried to fix Martian soil, washing out toxins, adding hydrogels, seeding Earth microbes. It was costly, water-intensive, and Mars refused to cooperate. Then Dr. Eris Thorne changed everything. Stop changing the soil, change the plant. His team gene-edited crops to thrive in Martian conditions. The Helios potato was the first breakthrough. Its roots broke down perchlorates, its leaves thrived under weak sunlight, and it barely needed water. We weren't just growing potatoes on Mars, we were growing Martian potatoes. Each new Helios crop was engineered for the environment. Tomatoes that extracted phosphorus, lettuce with deep roots for loose regolith. The plants became the solution, not the problem. As they grew, their roots broke down minerals and after harvest added organic matter to the soil. Instead of brute force, we had a biological toolkit. The soil improved with every generation. Martian farming became possible because we let life adapt to Mars. The crops were as much pioneers as the people, and they made the red planet a little greener. With crops ready, the next challenge was their home, Biodome Alpha. Not a dome but a semi-buried structure shielded by Martian soil from deadly radiation. Its polycarbonate roof captured sunlight. Fiber optics and LEDs filled in the gaps. Inside, a controlled atmosphere and ruthless water recycling kept everything alive. The AI farm manager, George, monitored thousands of sensors, adjusting water, nutrients, and light for every plant. Robotic arms pruned, tested, and harvested. George predicted problems before they happened, adapting to dust storms and nutrient shifts. Humans checked in, but the dome ran itself. Assembly was a ballet of autonomous machines, years in the making. When the first seeds were planted, the world watched. Every sprout was a victory. Biodome Alpha wasn't just a building, it was proof that life could take root on Mars, and it was just the beginning. Why go to all this trouble? Because a colony that can't feed itself is just an outpost, chained to Earth by a fragile, expensive supply line. Every shipment took months and cost a fortune. Early crews survived on freeze-dried rations, monotonous, demoralizing, and always at risk of delay. Food is more than fuel. It's comfort, culture, and hope. True independence required breaking the supply chain. Biodome Alpha proved it was possible. A self-sustaining food source meant the colony could grow, even survive if Earth faltered. It was the key to a real Martian city, and a backup for humanity itself. The humble Martian potato became a symbol of resilience. It carried the weight of our future, and it changed everything. The path to the first harvest was anything but smooth. 3 months in, a microscopic fungus, an Earth stowaway, devastated the tomato crop. The AI, George, couldn't identify it. The crew had to act fast, working for days to save what they could. Nearly half the tomatoes were lost, a harsh reminder of the ecosystem's fragility. The crisis forced a total overhaul of the AI's disease detection, making it smarter and more adaptive. Then a Marsquake broke a water pump. The backup was never meant for long-term use. Water levels dropped dangerously. Chief Engineer Kenji Tanaka 3D printed a replacement and made a risky repair. Each disaster taught the team to improvise, adapt, and trust each other. The psychological toll was real, but so was the bond it forged. Every setback made the project stronger. The final harvest was all the sweeter for the struggle. The first harvest was a planetary event. On October 12, 2050, the crew gathered in Biodome Alpha, the air rich with the scent of life. Commander Rostova dug up the first Helios potatoes, holding them up for all to see. The meal was simple stew and salad, but it tasted like home. It was more than food, it was a sacrament, a celebration, and a promise. This success sparked a new vision, terraforming through farming. Helios crops began changing the regolith, adding organic matter and breaking down toxins. Scientists dreamed of a future where billions of plants could slowly thicken the atmosphere and retain moisture. The innovations didn't stay on Mars. Water recycling and gene-edited crops revolutionized Earth's agriculture, helping drought-stricken regions and cities alike. In solving Mars, we learned to better care for Earth. The Martian harvest was just the beginning. It helped us tend our own garden on 2 worlds.